All right, today we're covering 7-3, which is logarithmic functions. So we're going to write equivalent forms of exponential and log functions, write and evaluate and graph log functions. And I guess first I want to define logarithmic function. It doesn't really tell you. We start out, you can write exponential equations as logarithmic equation and vice versa, but it doesn't really explain why you can do that and what it is. A log is basically the inverse of exponential functions. So last time we talked about inverses, and that's why we talked about it, so you could understand that this is the inverse of exponential. And if you look at this, you can kind of see, so we looked at exponential functions, exponential growth and decay functions, and we had some where we had something like a of t equals a times 1 plus r to the t. We had examples, we plugged numbers in here, and we wanted to find how many years or how many days. We wanted to solve for t. The only way we knew to do that was to graph it and do a trace to figure out when t got to the value that we were looking for. Now we have another way. If you see here, here's our exponential function with x, our variable, as our exponent. A log function, when you solve it, when you give it parameters, what does it give you back? It gives you the exponent back. So it's a nice way to be able to solve for exponents that are variables. And it shows you where things go. So log, this is called to the base b. And notice we called this base when we talked about exponential functions as well. So log to the base b of a equals 10. The example that I always use to help me with this is 10. So 10 squared is equal 100. So if I rewrite that, it's going to be log to the base 10 of 100 equals 2. I use this example and it helps me remember how the log function relates to the exponential function. What I get back is the exponent. This is the base I'm talking about. And then this is the number that I'm giving it. So this is telling me that 100 is equal to 10 to the second power. It might be helpful if you have one example like that that helps you remember. Then you don't have to remember this particular graphic, though having this is going to be very helpful. Notice also b has to be greater than 0 and b is not equal to 1, which we learned when we talked about exponential functions. So it says read log b of a equals x as the log to the base b, that's the way I've always learned it, of a is x. Log is the exponent. So as I said, when you use log, you're solving to find an exponent. All right, so it says write the exponential equation in log form. So you can write that graphic with the arrows showing you how things translate. I always just write this 10 squared equals 100, log to the base 10 of 100 equals 2, and then that helps me remember how things get translated. So this is, it's hard to see, 3 to the 5th power is 243. So I know this is going to be log to the base 3 of 243 is equal to 5. And I know that because I'm remembering this. All right, so remember, this is our b, and this is our exponent, or our x, and this is our a, is it? I can't really even remember myself. I just remember this. All right, so for this one, this is going to be log to the base 21, or 25, sorry, of 5 is equal to 1/2. Is that right? It has to be right. Yes. So that means 25 to the 1/2 power, or to the square root of 25 is 5. Here, this is going to be log to the base 10 of 10,000 is equal to 4. And then lastly, log to the 6th power of 1/6 is equal to -1. And lastly, log to the base a of c is equal to b. So your exponent is always on the other side of the log function. That might be helpful to remember. So notice every single time this side of the equal sign is my exponent. So that might be helpful. And you can see those are the answers they have. So I'd like you to practice as well. So if you would write these in log form and see if you can get these right. All right, now we're going to do the reverse. Write the log in exponential form. And again, I use the same template. 10 squared equals 100. Log to the base 10 of 100 equals 2. So I know this is my exponent. This is my base, so this is going to be 9 to the first power is 9. Exponent base, 2 to the 9th power is 512. Exponent base, 8 to the 1/3 power is 2. Exponent base, 4 to the -2 is 1/16. And then lastly, exponent base, b to the 0 is equal to 1. So again, I find this very helpful knowing this. This is easy to remember, and then you can kind of look at those and figure out what you need to do to any of the other ones. All right, so these are ones for you to try. See if you can write those in exponential form. Bring your questions. Couple properties of logs. For any base b such as b is greater than 0, b not equal to 1, the log of base b, so b, the log up to base b of b is 1. So log to the base 10 of 10 is going to be 1. So it means, and it's intuitive, it means this base to the first power is equal to itself. And again, they're using 10 as well because I think this is one that we can easily remember and understand. So log to the base b of b is 1. Next example, log to the base b of 1 is 0. So any number, any base to the 0 power is going to give you 1, and that's the only exponent that would give you 1. So 10 to the 0 is 1. 300 to the 0 power is 1. So it doesn't matter what base it is. If you're doing a log function of 1, it's going to be 0. All right, so you have a log button on your calculator, and notice we can have any number for the base. The common logarithm has a base of 10. So that's because I think it's most commonly used. What do you know? So if no base is written, the base is 10. So the default base is 10. So the log of 5 is basically the log to the base 10 of 5. And the one on your calculator is going to be base 10 as well. All right, so evaluate using mental math. So remember, we have 10 squared equals 100. Log to the base 10 of 100 equals 2. So this is saying what power of 10 is 0, 1? So how many, basically we are moving the decimal to the right 3 times. So that answer is going to be, should be -3, -2. Huh. So 10 to the -2, well 10 to the -2 is 1 over, yeah that's right, 1 over 10 squared, which is going to be 1/100th, which is what that is. All right, yeah, so this is how they set it up. 10 to what power is going to give us this. 5 to what power gives us 125. This one I do know, it's going to be 3, so 5 times 5 is 25, times 5 is 125. 5 to what power gives us 1/5? Well, this is a reciprocal, it's going to be negative, and it's 5 to the first power, so it's going to be a -1. So this is -2, 3, and -1. So I didn't have to use my calculator. I just figured out by figuring out what power of the base is going to give me the number. And those are the answers. So I'd like you to try this one, see if you can figure it out. All right, like I mentioned at the beginning, logs are inverses of exponents. So if you have y to the 2x, which is an exponential, the log function is going to be log, and remember this is our base, this is our input into the log function, and this is our, whoops, yeah. Oh, I didn't switch my x and y, that's why. So to write the inverse, I should have switched my x and y, and then you would get this. All right, so log function is y equals log to the base 2 of x. So if we graphed them, here is our exponential function, and as it says, x just keeps going in both directions forever. So domain is all real numbers. Y, you can see it, as we talked about in 7.1, it never is 0 or less. So y is going to be greater than or equal to 0. If we graph this function, this is this function, and you can see in this case y is going to go forever in the negative and positive directions. It's going to keep getting bigger and bigger. So the range is the real numbers. However, x is never going to go be less than 0. X never crosses the y-axis. So x is going to be greater than 0. Just like an inverse function, the domain and range swap. All right, use the values, graph the function. So these are our x values. And then we want to describe the domain and range. Oh, we want to graph the function and its inverse, and describe the domain and range. All right, so we're going to take these values, plug them in for x, and make a table. So these are our x's. When we plug these in for x, these are our y values. Here is our graph of that. And you can see here, we don't have to describe domain and range for the original, just for the inverse. So inverse, we don't need to even use the log function. We're just going to switch our x and y values. So here we have our x and y values switched. When we graph it, we've got this now. So if we look at the domain, you can see that x again is going to be greater than 0. It's never going to go negative. Y is going to go infinitely in both directions, so the range is going to be all real numbers. And this is one for you to do. Graph the inverse, graph the function, describe the domain and range of the inverse. All right, here's an application. The table lists the hydrogen ion concentration for a number of food items. I'm sure you have always been fascinated. Milk. So hydrogen ion concentration is related to pH. How is it related? Well, it's the log function, the negative log of the hydrogen ion concentration. So for instance, the pH of milk is going to be negative log of this very, very small number. How are we going to find that? We're going to put it into our calculator. So again, this is base 10, so you don't have to worry about the base. Put in negative log of this value, and you're going to get 6.6. So pH, oh, right, and the log key, hopefully you can find that on your calculator. So pH is about 6.6, which is somewhat interesting, I guess. So I'd like you to find the pH of tomatoes and lemon juice using this formula here. Make sure you know how to use your log key on your calculator. All right, that wraps up this lesson. Here is the homework. Bring any questions to class.